very difficult in 4 hours, which is what we gave ourselves for the scientific part of this conference, to do any justice to Selberg's great contributions. So we chose some topics that we thought were really important, but that was our choice. That's Enrico and myself. And we realized that if we weren't going to have a big conference, further scientific talks, then we were omitting many great things. So I'm going to try cover 3 gems. 2 are real gems, the third one's sort of a whole topic. I'm not going to be able to do justice to them, and worse than that, we're going to have to leave out many, many great things that Selberg did, published and unpublished, but that's the nature of such a memorial, which is a mixture of scientific activity and reminiscences. So let me start with the Selberg integral. That's the paper. It's paper 14 in his collected works. It was written during the war. It's perhaps, if I understand correctly, is a unique paper written in Norwegian, actually. So let me explain the context of this paper and then its history and impact. This paper is just a paper in calculus. It should be taught, I think, in all calculus courses these days. I certainly realize I've been missing a great opportunity in not presenting it in Calculus 1. I will next time. So, I still teach calculus. Euler, this is called the Euler integral, or beta function, evaluated that integral that you see over there, so this should be understandable by everybody. Just need to know elementary calculus. That integral over there, alpha and beta are real numbers or complex numbers, as long as it makes sense throughout here. And gamma is a gamma function, which is this, often called the Euler integral too, this integral over there. And that's a remarkable identity for which there are thousands of proofs, and many given in elementary books. Selberg's integral, well, the generalization of that was, there are generalizations, and the most obvious generalization is already here in Selberg's paper in the second line, due to Dirichlet, which is a multivariable integral, which looks very much like this integral, and the proofs, standard proofs, generalize to give that this integral is this ratio of gamma functions. What Selberg discovered was something quite far, far deeper, and it's the following multiple integral from 0 to 1, n-fold integral of x1 times xn to the alpha minus 1, and then you take 1 minus x1 times 1 minus xn to the beta minus 1. Again, alpha and beta are real or complex numbers, and gamma, as long as this makes sense, this is going to be an identity that's true. And the part that's a little more interesting here is the third factor. There's a new factor here, which is a product, the discriminant product of the differences ordered here of the xj's and the xi's raised to, in absolute value, to twice gamma. This integral is also a product of ratios of gamma functions as written over there. Well, it's hard to imagine that in the 20th century somebody is going to discover a new formula of this type. And Selberg, who actually got interested in this or found this because he was generalizing a theorem of Galfond about entire functions, which is an earlier paper, needed this. And he, during the war, and I guess wasn't able to determine whether this was known. So he remarks in the first paper that I need this. It's a little long, so I'll return to it and publish it if it's not known. But then he couldn't quite decide if it was known or not, and I think he spoke to some teachers of his, and he published it here as in Norwegian in what's something like the Mathematical Gazette, meaning for high school teachers, and put it there. And of course he didn't tell anybody, and it appeared there. The most striking thing about this is the form. He discovered the form, but it wasn't just discovered out of thin air. And I would say in all of Selberg's works, you always see a thread from one paper to the next. Very logical, nothing unrealistic in his steps. One thing leads to another, but when you're finished, it's always amazingly deep. Let me say a word about the proof, because it was kind of beautiful, simple. So if gamma is an integer, you can actually expand that, and you get a function So gamma is an integer, you expand the left-hand side, and you get a function which you can actually evaluate for all alpha and beta where it makes sense, using actually this Euler integral. You actually use that along the way, together with some nice symmetry arguments which are critical, and manipulations that are really nice, and you can find them in the original paper. There's absolutely no reason or way to improve that part of the proof. And once you know this for gamma, an integer, a positive integer, then being his love and actually where he was coming from, this theorem of Gelfand, he applies, or he reproves the theorem of Carlson here, which is that if you have two analytic functions in the right half plane which are bounded, or there's some weaker statements you can put, and they agree on the positive integers, then they actually have to agree. So the way you get this to be true for all gamma is you know it now for gamma an integer, and you know the right-hand side, the gamma function's well understood. You know both of them, the difference is now going to vanish at all integers, and you've got control on the size, so hence it's an identity for all alpha, beta, gamma, where it makes sense, in particular all gamma. So it's really nice, and he needed it, so he published it. It went completely unnoticed. I think it's referenced once in those years by McGregor and Carlin, who were doing some multi-dimensional integral. It resurfaces in 1979. This is why we know it today as the Selberg integral, when Enrico Bombieri had, or still has, a very beautiful idea of how to use such integrals and their coefficients, about the divisibility of certain coefficients associated with them in the connection with understanding prime numbers. And he wanted to evaluate this integral. Now, if I understand correctly, he had a chat with Tom Spencer, who suggested that Dyson might know something about this, since Dyson was writing down integrals associated with random matrix theory. I mean, this is really basic stuff, doing an integral, so it's going to come up all over the show anyway. So I think they spoke, and Enrico had the good sense to go ask Atle if he had any idea how to do this. And Atle's response, if I understand correctly, was, can you read Norwegian? Why? Well, I published this, actually, thank goodness, in 1944. And indeed, that was true, and that is how the Selberg integral became known to the world. Interestingly, in the meantime, people like Dyson and Mater, who was very good at this sort of thing, were trying to evaluate integrals of this type that I have over there. And they weren't able to evaluate it, so there were conjectures, as often happens. Conjectures are made based on theorems that were proved before. So Dyson and Mater had this conjecture over here from the 70s. The minute this became known, this was immediately no longer a conjecture. That implies this very easily by a simple limiting process that certainly Selberg even had in his notes. So this was immediately settled. It's a little more interesting that in 1982, McDonald, special function McDonald in England, generalized this Dyson-Mater conjecture and integral in a beautiful way, replacing the product of the differences of the xi's in this formula over here by taking a finite reflection group in Rn, reflection in a finite number of planes through the origin, and replacing the xi minus xj by the product of the distances from a point to these hyperplane reflections. And then delta gets replaced by p. This Gaussian is still the same. And he had a beautiful conjecture in terms of what should be the arguments of the gamma function in the right-hand side here in terms of the ring of invariant polynomials, particularly their degree. So it's funny that this information of this Selberg integral doesn't seem to have traveled to England yet by 1982, because he makes these conjectures. These became known as the McDonald conjectures. And the minute he found out about Selberg's integral, he could do 99% of the integrals of his conjectures. The groups there get kind of complicated. The final solution of the last case was done by Opdam only in Opdam, I think that's his name, in 1990. So this Selberg integral has become very important, as it should be, because it appears naturally in all sorts of places. But I first heard Selberg lecture on this in Berkeley when I was a graduate student. In his typical style, he saw now everybody was interested in this integral. He'd never said a word about it to anybody, so now he decided he'd give lectures on this integral. The room was packed, absolutely packed, and he got up and he said, I'm going to explain this integral that I did in 1944. Zero motivation, zero explanation why he's doing it. There was just shock. He's pulling out this paper from 1944 and just doing this integral. He didn't believe in motivating. I guess only fools need motivation, right? He did highlight at the end of the lecture, and this was clear to him, all these applications were, of course, this is why he was lecturing. He enjoyed it, there's no question about it. But I think there was one thing that interested him that he wasn't able to do in 1940, nor in 1980 when he was lecturing about this again. And that is he formed an analog, a finite field analog. So the Euler integral and the gamma function have very well-known finite field analogs. The Gauss sum is the gamma function. The Jacobi sum is that beta function. And so those, Jacobi explained, have finite field analogs. And Selberg easily formed the analog of his Selberg integral in a finite field. And he would end his lecture by saying, by formulating this, I just don't have time to do it, formulating the analog sum in a finite field and saying this he can't do. His method, which was elementary and beautiful, could not handle that except in the special case of n equals 2. And this, finally, 10 years later, was solved beautifully by Greg Anderson, I think a student of Washington here at Princeton, but he was trying to use very sophisticated modern methods until he finally understood that you could do this completely elementarily, and he even found a more elementary proof of Selberg's integral than Selberg's. Elementary enough that it worked wherever it was supposed to work, in particular in the finite field. And this, I know Selberg was rather impressed by, because, as I say, he would always finish his lecture saying he couldn't find that. If you want to see more about this, there's a beautiful account on this Selberg integral on the web by Forrester and Warner. I think I've misspelled Warner. Okay, that's part one, the Selberg integral. The second topic I wanted to cover very briefly is the Rankin Selberg method. This is an earlier paper of Selberg. It's a paper from 1940, again during the war. Also written in a Norwegian journal, but in German. Most of his papers were in German at this point. To answer Langland's, I think when Siegel said he had done 3 great things by 1951, I don't think this Rankin Selberg was one of them, even though I'll explain its impact in a second. I think he had in mind his work on the Riemann zeta function and L functions, a positive proportion of zeros, his work on the sieve, and his elementary proof of the prime number theorem. I think that's the 3 would be my guess. Okay, now, as I say, Selberg, this is very early on in his career. This is his 4th paper. There are 2 people he studied deeply. I know this from many discussions with him. One is Riemann, and the other is Hecker. And he was always very regretful that he never went to listen to Hecker's Congress talk in the Oslo meeting in 1936. He was 19, Selberg, and probably not as disciplined as he was later, and he missed this talk and hence never met Hecker, and he always regretted this. But he certainly had studied Hecker's work rather deeply. And Riemann-Jones, he's written about his sort of, he got a lot of inspiration from Riemann-Jones. And that's where this Rankin Selberg paper comes from. Now, Rankin is not a co-author with Selberg on this paper. Very few people are co-authors with Selberg. I think Charlo is the only real co-author in one paper. These papers were written separately. In fact, Rankin's paper appeared a year before. This 39, I think communications were very bad at the time. So these were done very independently, though the method is essentially the same. But this is, as you will see, Selberg's second paper on automorphic forms, but one which I think was at the back of his mind in all his later work on automorphic forms, and it certainly has played a massive impact. So let me just explain it in this very simple case so that everybody can understand what this Rankin Selberg thing is. Suppose we take the following function of q, delta. It's not the same discriminant there, but it's another discriminant. And we expand this expression, that to the power 24. We multiply out those products and collect terms. You'll get the following. This is Ramanujan's function. It starts out like that. Some tau of m q to the m. That's the definition of these whole numbers, tau of m. And Ramanujan notes in his paper on this function, tau, that if m and n have no common factors, then tau of m times n is tau of m times tau of n. Probably all of us would see that if we saw the numbers, but none of us, I would confidently say, would predict the second thing, that if you take any prime number p, tau of p is at most twice p to the 11 over 2. This is the famous classical original Ramanujan conjecture. This function is not just a random function, it's a function, it's the sort of typical automorphic form, a difficult one to handle. So if you write this number q as e to the 2 pi I z, so that z is in this upper half plane where all the theory of classical modular forms takes place, then the function has this transformation property that delta, this is of course classical, delta, this is what makes it a modular form, delta of az plus b over cz plus d is cz plus d to the 12. So these funny numbers like 11 over 2 and 12 have to do with a parameter that's associated with this function called the weight. But you should think of, just like we saw in the previous two lectures, delta is some kind of periodic function, automorphic function, where the elements in the group are 2 by 2 integer matrices of determinant 1, a big and complicated group, and that's the periodicity. So delta is a holomorphic cusp form of weight 12. And Hecker, exploiting and understanding this feature over here, that the first feature of Ramanujan, which was also Mordell made an important contribution there. Anyway, Hecker's the one who put this in the modern theory and understood all these things, formed a function out of these numbers tau of n. Tau of n over 11 over 2, that's the normalization associated with that weight, just to make those numbers roughly size 1. You can see the signs change, sort of randomly, times n to the minus s. So this is a paper before Selberg's work on the Riemann zeta function and L functions, but he certainly was interested in functions like this, like the Riemann zeta function. And what Hecker showed is that the function n to the minus s, that's a zeta function, we saw it yesterday, all the properties of the Riemann zeta function are shared by this kind of function. They have an extension, they can be defined for all complex s and satisfy a functional equation. That was Hecker's theory that Selberg had studied closely. And this Rankin Selberg paper was the first L function beyond what we would call today the standard L function associated with this automorphic form. Now, this is the form they would write it. It's not exactly the form you would write it today. This is not the notation they would use, but they, instead of forming this function, which gave the first serious new generalization beyond the Riemann zeta function and Dirichlet L functions of L functions, this is formed out of squaring the coefficient rather than just taking tau of n. And it is that much more difficult to show it has the right properties. And that's what the Rankin Selberg paper, the separate papers do in the same way. They show that this function has the same properties as Hecker's and as the Riemann zeta function in terms of their analytic continuation and functional equation. Let me say a word about the proof. There's, of course, a pole for this function. The proof, it's very simple once you have the idea, is it's a new integral representation, something that was extremely original, very short, easy, but once you have the idea, it's straightforward. You integrate over the quotient. So this group, this function has some periodicity, so you don't take the whole space, you take only the points that are different, so you integrate over the quotient, not the function, but the square of the function times the right weight, times some important new kind of object, which is interesting. This is called an Eisenstein series, named after Eisenstein. We heard this morning about Selberg's really profound work on Eisenstein series. This is one of those easy Eisenstein series, thank goodness. He didn't have to develop his whole theory of Eisenstein series to understand this, or he wouldn't have been able to do it in 1940. So this is Eisenstein series is explicitly that, and it actually is a name in this case. It's called an Epstein zeta function, which is what both Rankin and Selberg use in terms of their properties. So this Eisenstein series has the property that as a function of S, it makes sense for all S and has the functional equation property, and hence I of S inherits this. And because I in S inherits it, we can make use of the following, which we now, everybody who works in the subject calls this unfolding trick. Trick, I wouldn't call it a trick. Trick means you use it, once you use it enough times, it's no longer a trick, it's a theory. But it's a very important procedure which allows you, and it's straightforward, I won't go through it here, to express as I of S as some known factor times the function we want to understand. And hence we conclude the properties of the function we understand by understanding I of S, which in turn are understood by the Eisenstein series. This is the 3-page or 4-page paper. There's no need for any more in this paper. It opened the door. And its impact is what I want to talk about for the next 2 minutes. Well, immediately, why were they writing this paper? Today we look at this as much more important, but the reason they were writing the paper here was they wanted to solve this problem of Riemannian, of estimating tau of p. And this immediately gave the first, or actually a second, but what happens to be the first of a series of steps. The trivial upper bound for this is p to the 11 over 2 plus 1/2, and with this extra piece of information and standard classical machinery, you could improve that 1/2 to 3/10, a slightly smaller exponent. It's the first serious step in the right direction. They both got this estimation. It turns out that this step is a very important step in actually solving the whole problem, but not directly in this way. To form a more complicated function, you might think put 3 or 4 over there. That's not a good idea. It took many years to understand what function to put over here, what is the replacement of that, and it only came in 1967 when Langlands put forth a general, completely general set of functions that you associate conjecturally with a tau like this, which would generalize the Rankin Selberg in a sufficiently flexible way to obtain the full Riemannian conjecture if you knew the properties of those functions. The end of Arthur's lecture, the very end, the dream, the only game in town or whatever it was, is one of its big goals would be to understand the symmetric power L functions that I think he even mentioned for this Riemannian tau function. Well, this was a very important step even to define what the right objects are, because in terms of impact, Deligne in 1974 used this impact in an entirely different setting where this kind of machinery was beautifully developed by Grothendieck to prove the Weil conjectures. The Rankin Selberg idea was a critical step. It was a first step. The rest of the steps were completely analogous to what Langlands outlined would work over here. But in this function field setting where the Weil conjectures live, these ideas could be executed and were. And even the Riemannian conjecture itself was settled by a further set of remarkable identities, if you might want to call them that, which, by the way, are proved using the trace formula, a set of ideas that goes back first to Eichler. So the impact of this little paper of Rankin and Selberg was it played an important impetus in even solving the full Riemannian conjecture. The Rankin-Selberg method itself has been developed more generally and is a very, very basic tool, especially in more general groups. For n-by-n matrix groups, it's really critical in the classification and in answering all sorts of questions, and it was developed by Jacquet, Piatetsky, Shapiro, and Shalaika in a series of a couple of important papers where the method is very similar in terms of Eisenstein series as described there, but in general it's quite a bit more difficult to carry out, and these people had been involved in further generalizations. Okay, that's part 2. I'm just taking my 30 minutes. I won't be more. The third, I think it's interesting here, the third is about rigidity, arithmeticity. For some reason, and I think Atle, he told me that he was basically a lazy man. This was hard to believe, but I think he was explaining why he stopped publishing in the regular fashion at some point. Friedlander put it very nicely yesterday that if you asked him to lecture, and if he agreed, apparently not always, but when he did, then he would always have something new that he pulled out of his drawer. So I think the same happened with conferences. Every time somebody invited him to a conference and then put the screws on him to produce a manuscript for the proceedings, he would pull something out of his drawer with some remarkable new theorem. So all his publications after 1955, or so, that according to my looking at his collected works, are not in regular journals, they're only in conference proceedings. And two of them are the ones I want to mention here, and they are about rigidity. So there's no doubt he had these ideas for some time, but for some reason, I think had enough with the process of ordinary publication. Okay, so let me explain the remarkable insights here. And to me, this is most striking because this was not a field in which he was trained or anything, but where he went and he immediately saw what might be true and then spent a lot of effort trying to prove it and making the right conjectures. So his work in automorphic forms led him to the study of quotients of groups, semi-simple groups, divided by subgroups which had finite volume as a quotient, so what we call a lattice. You don't need to know what the general group is here to see the features I'm going to describe. Just think of SL and R, n by n matrices of determinant 1 with real entries, and the subgroup, which is going to be of that nature. Here's a good example, SL and Z, n by n matrices determinant 1 with integer entries. That is finite volume quotient. That's been known for many years. And in the case of the upper half plane, as Henrik pointed out a number of times, there are many well-known methods to construct families of discrete groups and quotients. This comes from the uniformization theory, from the theory of Riemann surfaces, moduli that has been known since the 1800s, certainly early 1900s, with the study of deformation theory of discrete groups. So it was well known that you can deform and that these objects come in families. On the other hand, if you went to a bigger group like SL3R, then the only examples that were known were these ones like SL3Z, which we call arithmetic, or things closely related to it. I'll be vague here. And these were deeply studied in great detail by Siegel in connection with the theory of quadratic forms, for example, in symplectic geometry. And the main paper on arithmetic groups and their structure was by Borel and Harishchandra. So that's what was known in the late 50s when Selberg asked, and others, as I'll explain in a second, started to ask, well, what is the story in this higher dimensions or higher rank? And Selberg studies the following problem in the first paper over there, that if I take a family of such groups, and a family just means that I have gamma t, t is a real parameter, each gamma of t is isomorphic to gamma, so it's a deformation, it preserves being a lattice, it preserves being discrete, and so on. And can I deform this non-trivially? I'll show you what a trivial deformation is. What's the deformation space of such a group? He asks that question. And he answers it that for n greater than 3, there's an amazing change. This is quite striking. He shows that every deformation, if n, I'm talking about now SL3R or SL4R, unlike SL2R, every deformation is given simply by taking an element in the group, call it G of t, and conjugating T inverse gamma. GT is going to be a new subgroup of the same properties, but because it's conjugation, it's geometrically, or in every sense of the word, no different. So every deformation is trivial, or the group is locally rigid. He proved this if it's a compact quotient of SL3R, the easiest case for this kind of analysis. And secondly, he proved, and this is really what he was after already at this early stage, he showed that every such group can be conjugated so that all the elements in the group are entries which are algebraic numbers in a fixed number field. The number field depending on the group you started off with. So it's a first sign that these things are extremely limited once you get away from SL2R. In SL3R, everything is algebraic in a fixed number field, at least if you compact quotient. He obtained many more general versions of that, but there were serious technical problems if you were only finite volume rather than just co-compact. In the meantime, and I suspect by reading, I read the introductions to all these papers in the last week, Calabi and Vicentini gave a geometric proof of not all, of something, this is for real rank greater than or equal to 2, SL3R, for example. They dealt with hyperbolic spaces, which are rank 1, which Selberg, I'll say a word about his method, didn't discuss, but of course was very interested in. But by entirely different methods, basically computing deformation spaces, Calabi and Vicentini proved a similar local rigidity for hyperbolic spaces, for example, around the same time. And then they used Selberg's method to prove this part 2, which Selberg, I think, was particularly interested in. They didn't get the general case, nor did Selberg. It was in the co-compact case anyway. They then obtained the general case in a paper that appeared probably a year after those. So that was local rigidity, and it was, I think, quite unexpected perhaps, and certainly something very different. Let me say a word about Selberg's proof. It made use of certain centralizers, so he was using a higher rank property of SL3 or SL4 by looking at centralizers of certain elements which were basically tori, but higher dimensional, and their quotients, G gamma over gamma gamma. G gamma is the centralizer in G of gamma, that's his notation. And in particular, their behavior at the boundary of the corresponding space. So there's a corresponding symmetric space, and he understood, or his method applied by going to the boundary in order to understand a certain feature which led him to this local rigidity. If I understand correctly, at least from Mostow's writings, he was inspired by this boundary behavior, but felt that Selberg wasn't exploiting it enough, and amazingly found a much stronger form than this local rigidity. And this goes by the name of strong rigidity due to Mostow, which in the rank 1 case was first proved in 67, the general case in 73, that as long as you keep away from this group SL2R, which is very different, then not only are there no deformations, but you have a much more beautiful and striking statement that if the two groups are lattices are isomorphic, then they are actually they actually are isometric, the two spaces, so the isomorphism extends to an automorphism of G. This is really a geometric theorem, a very powerful theorem. It's fantastic in connection with the work of Perelman, where we understand three manifolds. If you have two hyperbolic three manifolds, they are completely determined by their fundamental group from this theorem. This is a beautiful theorem. But Selberg was really, in 60 to 68, I think, was really thinking deeply about this other question of, well, what about, I've made these things algebraic numbers in a fixed number field, and he understood that if he could bound the denominators in this proof of his that you could always make the numbers algebraic, he could actually then show that the group that you were looking at was not just any old group, but it was actually arithmetic. In other words, the only constructions that you know of how to make them were the ones that exist. And he was really after that, and he made what I think is an extremely bold conjecture, that if the real rank of the group is greater than or equal to 2, then gamma is arithmetic. This is his famous arithmeticity conjecture. And I find this to be quite striking. It's bold. I asked him once, how did you come up with this? He said, well, he couldn't make a counterexample, so it's probably true. Yeah, I think Mostow put it nicely last night. He did not lack in self-confidence. Well, Selberg doesn't make a deep conjecture like this without a serious theorem towards it. And he did prove one case of this. And I think it's not so well known, so let me point this out. In the second paper that I put down there, he actually gave a complete proof, which is outlined in this paper, but it certainly was obtained during that period. that if you have a subgroup of the product of a number of upper half planes with at least two factors, you need at least two factors, because if there's just one factor, we're back in this problematic case of the upper half plane. If you have at least two factors, and you're irreducible, that's some technical condition that you don't sort of reduce back to the product situation. And an assumption that was a harsh assumption, you're not compact. So in this case, he assumed that you actually are specifically not compact. So there are cusps. And he was able to understand those cusps, partly by, he learned some work of Piatetsky-Shapiro, which was helping him here as well, by the way. Anyway, using that, he was able to prove that the group is arithmetic, not only arithmetic. It was basically a Hilbert modular group. I put a star here, and this is why I think some people think he didn't, well, maybe, his proof was conditional on the generalized Riemann hypothesis. So it doesn't sound like he proved it, right? Although, what's that got to do with this? This is apples and oranges. We should understand this is a major piece of progress. Around that time, the work of Bombieri-Vinogradov came out, and he understood immediately he could make this proof unconditional, but he didn't bother to write a paper doing that. He just pointed this out verbally to a few people. So, in fact, his proof is unconditional. All right, so that was a case of when you're not compact. Margulis and Kashdan solved these technical issues of what quotients which are not compact look like, and then using that, Margulis was able to completely prove the arithmeticity conjecture in '69 for the non-compact case. But the compact case looked much, much deeper and out of reach, and Margulis shocked the world, I think, with his famous '74 announcement at the Congress, which Mostar called super rigidity, which led to the complete solution of the Selberg conjecture. And of course, this was quite remarkable. And it's stated in terms of a extension to the boundary, but to say one word that was really fundamentally new in Margulis's work is you didn't try to extend the map from gamma, which was just, in this case, a homeomorphism, into a general linear group. And the important thing here is that K is a local field. In other words, where everybody before was working with real groups, Margulis understood that this boundary behavior could be used to understand such maps where this is into a p-adic group, for example. And eventually that, in this theorem, which I don't describe of Margulis, but his superrigidity theorem, you actually do understand the boundedness of the denominators and hence prove this fantastic conjecture of Selberg when the rank is greater than or equal to 2. So I'll end by saying there was an amazing further development. The differential geometric methods that Calabi and Vicentini started and that they carried on were about local rigidity, didn't stand still, and in fact, Sieve gave a proof, a global a differential geometric proof of Mostar's theorem in complex hyperbolic space, compact case, by using harmonic maps, a very, very beautiful idea. But it was just a new proof. And then a young man, Kevin Corlett, who's at Chicago, came in 1992 with a very major breakthrough by realizing that this global differential geometric method, which is based, as I say, on harmonic maps, nonlinear variational problems, in certain rank 1 spaces, not complex hyperbolic space, but in two unusual rank 1 spaces, quaternionic hyperbolic space, SPN1, and the Cayley plane, he made a very simple but far-reaching observation that if you harmonic, in the sense of a harmonic map, then you parallel. The equations to be harmonic in this case give you much, much more information than normal. Normally there are many harmonic functions, harmonic maps, but here you got this extra remarkable piece of information. And adapting Sieve's proof to this case, he was able to prove Archimedean superrigidity for these rank 1 cases. I should say that in Selberg's paper, one of the papers, he said he wasn't aware there were any other rank 1 spaces. So this is not part of his conjecture, but it is remarkable. And this quickly led, this was not trivial, to extend Corlett's work to the p-adic image case, but it was done by Gromov and Shane, and then led to the proof of Selberg's conjecture, the arithmeticity, even in these 2 cases of rank 1, not just higher rank. And in 1987, at Selberg's 70th birthday, Piatetsky-Shapiro brought him a present, he and Gromov had given examples of non-arithmetic lattices in every hyperbolic space SON1. Unfortunately, for his 90th birthday, nobody provided him the situation for SUN1, which I think is probably what the case is, so SUN1 remains unsolved. To me, this particular work of Selberg really shows that whatever he thought about, he saw very, very deeply. Really unusual. Thanks.